So another thing we need to talk about is molecules and polarity. Now remember we have already talked about dipole moments and polar bonds. So basically a molecule that has no polar bonds in it cannot have polarity. It cannot be a polar molecule. But if a molecule has a dipole moment, that is, it has polar bonds, and it is in the right shape, it can actually be a polar molecule or have certain portions of the molecule with higher density of electrons. Okay, so it depends both on the polarities of the individual bonds and on the geometries of the molecule. Now we'll do some modeling and some, actually I'm going to probably bring balloons in when we talk about these concepts. In the class, and it'll be easier to see, but I'm going to make an attempt in this video to discuss it so you guys got a good idea of what I'm talking about in class. So remember, right here underneath each of these atoms, I'm showing the electronegativity. Remember that anything that has any two atoms that are bonded that has a difference in their electronegativities that is greater than 0.5 or greater will be a polar bond. Or if it's a lot greater, it would be an ionic bond. But for this particular this particular video, we're talking about polar bonds. Now, if you consider the direction of the polarity for these bonds, of course, the electrons are being pulled towards the oxygens here. But consider the shape of this molecule here. The shape of the molecule is it's a linear molecule. If you looked at the electron domains, there are two electron domains. Anything with just two electron domains around it has a linear shape. And so because of that, this is a linear molecule. And so if you consider the electrons from this carbon being pulled this direction by this oxygen and being pulled that direction by that oxygen, the essential net effect, if you think about it, is zero. In other words, if there's a strong man trying to pull the electrons this way and a strong man, equally strong man trying to pull the electrons that way, the electrons will just stay in the center and just kind of be stretched out, okay? And that's what we see. And then the molecule is considered a nonpolar molecule. So these equal and oppositely directed dipoles, the bond dipoles, will actually cancel each other out. Even though we have polar bonds in this molecule, the molecule itself is nonpolar. So if you look at an electron density for this molecule, you'll see that there's a low electron density at the carbon and then higher electron densities at the ends, but these electron densities will have a net zero effect. There'll be no direction where you'll have a high negative charge or a low negative charge. It'll be on opposite ends of the same molecule. So if you think about polarity for something like water, remember water has these lone pair electrons up here, so here and here. And remember, we often draw those kind of like this, showing that, and that's why water has this bent shape here. So the electron geometry is tetrahedral, but the molecular geometry is bent. And so if you consider the electronegativities for oxygen and hydrogen, you see that it's obviously polar bonds. This is a polar bond. And so there's a polarity with the electrons moving in that bond, moving up towards the oxygen this way and up towards the oxygen this way. And you think about the net pull from these. Well, the oxygen pulling this way and out up to here will cancel the amount from the oxygen pulling this way. So these will cancel each other out left and right. But there'll be a net polarity straight up, because some of these have a little bit, if you've taken physics, think of it as vectors. You have a vector that is not canceled, that just goes straight up from these. So if I remove the ink, this stuff that I poorly drew on this molecule, and show you, see how the dipole bonds are moving up and up, they'd cancel each other just left and right and would end up with this dipole, or this polarity on this molecule that goes straight up towards the oxygen and would continue up this way. And we call that an overall dipole moment. We call that a dipole moment. And the overall dipole moment is just straight up through the oxygen. So these polar bonds don't cancel each other because they're not symmetrical about some axis. Well, they are symmetrical, excuse me, but they're not. They're mirror images that are pulling in the same way, in the same direction. And so we would consider this a polar molecule. So if we look at some of the other options for polar and nonpolar molecule, we consider BF3. BF3, remember this is, if you look at this, this would be a trigonal planar molecular and electron geometry. It's all of these are pulling out towards the fluorine, so it's pulling from the boron towards the fluorine, and because of that you get these dipoles in the bonds. But because this dipole is pulling this way, this dipole is pulling this way, and this dipole pulling this way, and it's symmetrical about that boron molecule, they'll end up essentially canceling each other out. If you look over at NH3, NH3's got that lone pair up here, and so you have a polarity towards the nitrogen. Again, because we have these hydrogens having their electrons pulled towards the nitrogen, you will have a cancellation left and right, but you'll have a net dipole, an overall dipole moment that will be pulling up towards the nitrogen. And finally, this CH3Cl. Remember, carbon and hydrogen do not have a polar bond. But overall, the dipole moment will be towards the chlorine because it is much more polar, or it's more polar than carbon, enough so that you have a polar bond this way. You have no polar bonds for these carbon-hydrogen bonds, and so the overall dipole for the molecule is up towards the chlorine. So that's what we mean when we talk about molecular polarity. It depends both on whether there are polar bonds and whether the symmetry of the molecule would cancel of the polar bonds would cancel each other out.